keep in mind that all this was going on while some big and bold ideas were happening in calculus. I showed you the example with a circle and cutting it up into infinite many little triangles. Perhaps some of you may be familiar with this example where you've got some sort of curve, and what you're trying to do here is you're trying to, let me see, I can add a little color here. You're trying to cut this thing up into infinite many little tiny rectangles, super tiny rectangles. Same idea as this circle, except it could be applied to any curve and some function in some region. And the idea is, again, you're trying to find the area under the curve. This is a central problem. This is why all this is happening in our calculus class. What happens here is you're trying to add infinite many of these rectangles. They're almost just like thinner than a hair. That thin, thinner than that. They're infinitely small. Each approximately 0 area. And so you're trying to add infinite many things that are, roughly speaking, 0 in area. So that type of calculation looks like infinity times 0 again. Same principle as the circle, the cut triangles. And that presents the problem now. We've got no choice. We've got to learn to play with these numbers here. We've got to dominate infinity and 0 so that we can ultimately solve the problem we want to solve, and that is the problem of the area under the curve. Okay, so that brings us to the solution. Now, what happened? How did we finish resolving this type of creature here? The infinity, or the infinity times 0, or some of these other ones that I talked about earlier. Infinity minus infinity. Well, now we've established the problem. We established the reason why we need to solve it. Now we need to establish the solution. How do we come about solving this type of problem? And the answer, I think, comes in trying to take a look at a new and more powerful view of real numbers. Okay, this will help, I think, understand a lot of the ideas from indeterminate forms. Not just memorize what the indeterminate forms, but really try to understand what makes them indeterminate. So here, let's have another look at numbers. Forget about numbers the way you used to think about them. Perhaps you used to think about 5 as just 5. 5 is just 5. Forget about it. Now we're going to think, or 7 is just 7. Forget about that. From now on, we adopt a different point of view, a more powerful point of view that says, no, these are not just numbers, they are equivalence classes. That's just a fancy word for, you know what, this is going to be a bucket of numbers. 5 is no longer just 5. It's a collection of a bunch of numbers. And the numbers that go in this bucket is everything that's very close to 5. So 4.99999 with a bar, that goes in there. 5.0000 with many zeros and a 1 there, that goes in there. How many? Many. More than, give me any number more than that. 5.00000 with a 2 at the end, that also goes in the 5 bucket. And so on and so forth. Everything that's really close to 5, that's in the 5 bucket. So you don't longer think about 5 as 5. It's the 5 bucket. It's everything that's really close to 5. And the same thing for 7. You think about 7 as all the numbers that are really, the collection of all possible numbers that are really close to 7. And I'm simplifying the ideas here a bit, just to make them super accessible for anybody. There's just buckets of numbers really close to 5 and really close to 7. The fancy name is equivalence class, and the fancy way to determine whether or not they're in the bucket is, or the collection of things in the bucket is this collection of sequences whose limit converges to 5, if you're interested in reading that. That's the fancy way of saying it. Anyways, for our purposes, we're going to call them buckets. And the way we're going to do arithmetic in this bucket is like this. 5 plus 7. Anything from the 5 bucket plus anything from the 7 bucket would give us something from, of course, the 12 bucket. And a lot of the arithmetic is just the same as before. Anything from the 5 bucket times anything from the 3 bucket would, of course, give you something from the 15 bucket. And so arithmetic becomes more or less the same, at least for the natural numbers, at least for the numbers that we were comfortable with, the 1 dog, the 2 dog, 3 dogs. Nothing's changed there, even if you look at them as buckets. But something profoundly changes when you look at these difficult other questions like dividing by 0 and whatnot. You get a much more powerful view of them and a better chance of intuitively understanding what's going on. Because watch what happens when you try one of those. Suppose I have 0. Suppose I have the 0 bucket divided by something from the 0 bucket. I say, whoa, what happens there? Usually you would have just said 0 divided by 0. Today we're looking at it as something from the 0 bucket divided by something from the 0 bucket. What in the world is that? Well, there's so many things in the 0 bucket. Let's just give it a shot. What if this something, the one thing from the top was 0.00000 with a bunch of zeros and then a 10, and then the one on the bottom was 0.0000 with the same amount of zeros and then a 5. Well, you'd say, oh, that's equal to 2. Okay, sometimes the point of this is sometimes a little tiny number, something really close to 0, divided by another little number, so really close to 0, sometimes that's equal to 2. I say, well, yeah, but that's not always the case, because sometimes it's not. You could have something else from the bucket. Maybe I have 0.0000, I don't know, 20, and then I have on the bottom 0.000005. Oh, sometimes a little number divided by a little number, they're both super little, but sometimes the ratio is 4. Yeah, sometimes I could have. In fact, if you think about it, it really could be anything. I could have 0.000001 over 0.000007, and in this case it's equal to 1/7. The ratio is 1/7. Really, if somebody just tells you, hey, I've got a super small number, something from the 0 bucket, it could even be negative, by the way. That's also in that 0 bucket. This 0 bucket is the only one that has positives and negative numbers in the same bucket. So if somebody says, I've got a super tiny number, something from the 0 bucket, divided by something else from the 0 bucket, what do you think the answer is? It's not as clear as these ones over here. These ones were super clear. No matter, it absolutely does not matter which number you pick from the 5 bucket. If it's really close to 5, and this one is really close to 7, I guarantee that the answer, when you add them, will be really close to 12. There's no ambiguity. It does not depend on which choice of representative you pick to carry on your calculation. This is a totally different animal. Here, when you say I've got a small number, something from the 0 bucket, divided by a small number, something from the 0 bucket, you must conclude, well, it depends, because not all zeros are created equal. It depends on how little the 0 is on the top and how little the 0 is on the bottom. And so that establishes as something very important. I just said a very important word that I want to, or phrase that I want to emphasize. I said it depends. It depends. 0 divided by 0, well, it depends on how little the 0 is and how little the 0 is on the bottom. Every time you're trapped into this corner where you don't know and you have to say, well, it depends on which one you pick from the bucket, the fancy name for that is called an indeterminate form. An indeterminate form. It's another way of saying it depends on which representative you pick from the bucket. That's what we call an indeterminate form. You could also say not enough information. I need to know what kind of 0 you've got on top and what kind of 0 you got on the bottom, because clearly not all zeros are created equal. That's the heart of it. That's the indeterminate form. Here, I'll give you another example. Suppose you've got, let's go switch back to white. Suppose I've got infinity minus infinity. Today we have a more powerful point of view that helps us make sense of this. It says, hey, I've got something from the infinity bucket minus something from the infinity bucket. That means something really big minus something really big. What do you suppose it would be? You can't say infinity, because what if this was exactly the same type of infinity? It doesn't always have to be, but it could be. Then it could be 0. What if this was infinity plus 1 minus infinity, where these two infinities are the same type? Well, in that case it was equal to 1. Or what if this was a 5? Well, in that case it was a 5. What if it was a 15? Well, in that case it was a 15. It really could be anything. What if this was infinity to the infinity, and that's a much more powerful infinity? Because again, not all infinities are created equal. This would be negative infinity. So the conclusion must depend on which item you pick from the infinity bucket and which one you pick from the infinity bucket. It is definitely not like these ones where it didn't depend. Something from the 5 bucket times something from the 3 bucket. Nobody can argue. It'll be really close to 15. Here, all bets are off. It is so different. If I have a large number, like, you know, and somebody else has another large number, all bets are off. Like I could say, yeah, you know, I think I have a lot of money. I'm kind of a millionaire. But then you compare me with Bill Gates. Well, forget about it. He has a lot more money than me. And so not all millionaires are created equal. I'm just kidding. Not all big numbers are created equal. There's some big numbers that are really big, and so this must be inconclusive. And you say you're trapped into this corner where you have to say it depends. It depends. It depends on which representative from this bucket, and if you were being fancy about it, which sequence that whose limit is infinity you pick from this equivalence class of sequences whose limit is infinity. You pick from here, and which one you pick from there. Or in layman terms, you say it depends. We don't know. More information is needed. More info is needed. Or the professional or the traditional way of saying it, we just say indeterminate form. Indeterminate form. That's one of the famous indeterminate forms. Okay, there are 7 in total, 7 indeterminate forms. And I think I'll let you just digest this for a little bit, and then I'll finish the 7s in the next video. Let me just leave you with one more thought here. Infinities will fail when you get these indeterminate forms, and that will need a remedy for when the buckets fail when you have indeterminate forms. And the remedy comes, of course, from how do you know when you don't know? Well, first, yeah, you gotta figure that out. We'll come back to that in the next video. It should not depend on which item you pick from the bucket. If it does, then if it depends on which item, then you've got an indeterminate form. And of course, the thing I wanted to leave you with is that the perfect medicine for indeterminate forms is the idea of limits. Limits will help us make sense of certain ratios or something, to see how big each one of the items was. If you have infinity over infinity, it's hard to gauge it, but if you try to see what happened before you got there, you might have a chance using the idea of limits. Limits is the prescribed medicine for the indeterminate forms. And so that should tying together a bunch of different ideas. What are indeterminates? Why are there indeterminates? The buckets of number, more powerful B of numbers, and limits. Where do limits come in? They come in to cure. Their whole purpose in life is to cure the indeterminate forms. Okay, that's the whole purpose in life, to cure the indeterminate forms. To see what's happening before you get there. Assuming that it's nice even before you get there. Anyways, next video we'll come back and try to talk about all 7 indeterminate forms and the perfect medicine, limits. See you guys here next time. Peace.